So we moved on to part C of our rotational kinetic energy problem, and part C says that someone throws a sphere with a radius of 0.01 meters or 1 centimeter and a mass of 5 kilograms at the other end of our rod where it sticks and deforms. And we want to know what is the new moment of inertia. So we're not being asked for the rotational kinetic energy anymore. We're just being asked for our new moment of inertia. Because if we wanted to calculate the rotational kinetic energy, we now have 3 objects in our system that we would have to consider, and it would all be one big jumbled mess. So we're just being asked for the moment of inertia of our rod plus our mass plus this new deformed sphere that has been thrown and has stuck to our rod. So we can just draw this out real quickly as well. Just like before, we had this rod, our axis still in the middle, and we had our mass on this one end, but now we had this tiny sphere, only with a radius of 1 centimeter, come in and just stick itself and deform on the end of our rod. So let's just start writing out what we know about our moment of inertia so far. So we have this total moment of inertia that we're going to get, and this is going to be equal to the moment of inertia of our rod plus the moment of inertia of our mass on the end plus the moment of inertia of our deformed sphere. So we, of course, know that the moment of inertia of our rod is 1/12 times the mass of the rod times the length of the rod squared. And then we have the moment of inertia of our mass from before, which of course was the mass of our mass times the distance from our mass to the axis on which the rod and the mass spin, squared. And then we have the deformed sphere. So the thing about this that people often get confused about is that this sphere, if it were rotating on its own, would have its own moment of inertia, the moment of inertia of a sphere. But what we have is that it sticks to our rod and it deforms. So it's no longer a sphere, it's stuck to our rod, and we can't really count our sphere, our tiny sphere, as its own separate entity, as a moment of inertia of a sphere, because it's not really a sphere anymore. So what we're just going to do is we're going to count it as another mass stuck to our rod. So this is going to be the mass of our sphere times the distance from the deformed sphere to our axis of rotation squared. So just like our deformed mass, we're just counting it as another, mass stuck to our rod. But anyways, with all of this written out, we can just plug in all of our numbers and then calculate our total moment of inertia. But basically what we've been wanting to understand is that any new object added will have its moment of inertia added to this big list. And if we were to calculate the kinetic rotational energy, our number would increase again because we're just adding more and more objects to our system. But anyway, we can write out all of our numbers. So 1/12 of 10 kilograms times the length of our rod squared, which is 4, 2 squared is 4, plus the moment of inertia of our mass being 3 kilograms times 1 squared, because once again, the distance between the axis and the mass was 1 meter. And then moving on to our tiny sphere at the end, this distance, our r, is going to be the same as the one for our mass, just because these distances are the same. So our sphere's mass was 5 kilograms, and then times 1 squared again. So we can just multiply this out and then add these two numbers together. 3 times 1 is just 3, 5 times 1 is just 5, etc. So we can calculate this out real quick, and what we end up with is 11.33, and then the unit for moment of inertia is kilograms times meters squared, because for all of these we have a mass times a unit of length squared. So with this number we have calculated the moment of inertia for our 3-object system, and as well we have finished our problem.